Bonjour and welcome to our lesson on radioactivity. So this is me talking through the first bit of the topic. I split the topic up into 3 sections. This is the basics about radioactivity. Next lesson we'll look at things like photons and excitation, and then the third and final lesson will be uses and things like that. So yeah, I'm going to talk you through the basic structure of the different types of radioactivity, the chemistry behind it, decay equations, activity, half-life, things like that today. There is a fill in the gap sheet which you are more than welcome to fill in as you go along, but you don't have to. That's purely optional. I know some of you like it for revision, some of you just want to crack on, but yeah, hopefully this reminds you of everything you need. So first bit is a bit of basic chemistry. Although the formatting's gone a bit funny here. Should we move this down? That makes a bit more sense. So atoms of the same element with different numbers of neutrons are called isotopes. The reason that is important is you may have one isotope of an element which is radioactive and one isotope which is not. Obviously, we really care about the ones that are radioactive at the moment. If you have a chemical symbol, the top number, or rather I should say the larger number, the mass number, is the number of protons and neutrons, or can be called the number of particles in the nucleus. And the smaller number is called the proton number or atomic number, and that's the number of protons that can be found in the nucleus. So the 3 basic types of radioactivity are alpha, beta and gamma. We do not say beta because we are not American. So yes, alpha is our biggest, slowest, heaviest, most charged type of radioactivity. It's made up of 2 protons and 2 neutrons. It is occasionally referred to as a helium nucleus because a helium nucleus also has 2 protons and 2 neutrons. It is incredibly ionizing, but it's not very penetrating. So I think we've talked about this back in the day when if you are wiped with an alpha source, you will be severely damaged by that alpha source because it'll be on your skin and it'll ionize your skin. However, if I was to stand 2 meters away from you, or even, let's be honest, a few centimeters away from you and point an alpha source at you, it wouldn't really reach you because it would ionize the air between you and I and not reach you. So not dangerous from a distance, but very ionizing in that short distance. Beta is a single, now most importantly here, it's a high-speed electron. It's not just an electron that hangs around, it's a high-speed electron. It is less ionizing than alpha, but it is more penetrating. It's got a charge of -1, obviously, what with it being an electron, and a fairly small mass, but it does have a mass. And the last one is gamma, which is an electromagnetic wave. It is not as ionizing as alpha or beta. It does not have a mass, it does not have a charge, it is just pure energy, effectively. But it is the most penetrating out of the 3. So talking about penetrating, here we go on to what stops the different types of radioactivity. So if you have a look at the top there, skin or paper stops alpha. As I say, not very penetrating, doesn't get very far. Beta needs to be stopped by thin aluminium. It will be able to go through paper. Gamma will go through skin and paper, go through aluminium, and then thick lead, or actually concrete as well, but you need meters upon meters of concrete, reduces gamma. So that's our best kind of defense against gamma, but it's not perfect. So why may a nucleus decay? It may decay if it is too big. Too many particles, let's get rid of some of those particles, you'll do alpha decay. Has too many neutrons, you've got a choice here, beta decay or neutron emission. I know we haven't talked about neutron emission. Full confession, it's just really dull. It spits out a neutron, that's it. Not really ionizing, doesn't really do much. Or it may have too much energy, in which case it'll do gamma emission. Now you need to know how the nuclei change when they emit these different types of radioactivity and be able to fill them in what we call decay equations. So this is what we're going through now. Alpha. If a nucleus gives out an alpha particle, the mass number will decrease by 4, the atomic number will decrease by 2. Please notice, because the atomic number has changed, that means the number of protons has changed, and elements are defined by their number of protons. So the moment you change the number of protons, you need to change the element symbol as well. So here, uranium's turned to thorium, because it's now got 90 protons. Beta, now for a reason, in fact I'm going to write on this, what happens is the mass number remains the same, fine, but the atomic number increases by 1. Now the reason for this is inside the nucleus, make this a little smaller, and why not make it yellow? Inside the nucleus. A neutron turns into, in fact, let's do this as a chemical symbol. A neutron turns into a proton and a beta particle. Now, the beta particle is emitted, that's obviously there, but the proton stays in the nucleus. So beforehand, you had, here, 8 neutrons, 6 protons. After this, you've got 7 neutrons and 7 protons, because one of those neutrons is turned into a proton. If you do A-level physics, you'll look at even smaller particles called quarks, which make up neutrons and protons. And you'll see the fact that a neutron can turn into a proton because one of the quarks inside it has changed what we call flavour. I can't say the word flavour without thinking of Craig David, which is probably far too old for you, but in my head all I'm hearing is, what's your flavour? Tell me what's your flavour? Woo! Yes, there you go, a nice little treat for you. So yeah, there you go, beta particles, probably the most complicated one. Now, neutron emission, I told you, very, very dull. The mass number decreases by 1 because you have 1 less particle in the nucleus, and the atomic number stays the same because protons are not affected, and it just spits out a neutron. That's it. I haven't really seen any questions with neutron emission. This was a new addition to the specification a few years ago when Gove changed it. As I say, yet to see any questions on it, but obviously we include it just in case. Gamma emission, nothing happens to the nucleus other than the fact there is less energy. That's it. So gamma emission is done when the nucleus is what we call metastable, and it has too much energy. It will release that energy as a gamma photon. So ionizing we've talked about before, but let's just give you a bit of a definition. Ionizing radiation, like alpha, beta and gamma, you do also get X-rays which are ionizing, can remove electrons from atoms, turning them into ions, hence ionizing. This can cause mutations in your DNA or kill cells in your body, which can cause cancer and leading on to that. Activity. The activity of a radioactive source can be measured using a Geiger counter. It is the number of nuclei that decay every second. It is measured in becquerel, after a French scientist called Henri Becquerel. 1 becquerel is 1 decay every second. Lovely. The activity will decrease over time. Now, this is a key definition here. In fact, there's 2 definitions. The half-life of a radioactive element is the time that it takes for the reactivity to half, or the time it takes for half of the number of radioactive nuclei to decay. Now, that's just a statement, but it is something you need to be able to use in questions. So I'm going to talk you through how to do a question now, a half-life question, and how I got actually my year 10s to lay it out. As I'm sure you remember, people really don't like these type of questions, but I actually got my year 10s to lay it out in a way that they were all quite happy with when they did it this year. So I feel like I've cracked it in terms of the teaching bit. So I reckon we can do it together. In fact, let's do this one first. So here we have a graph, counts per minute on the left-hand side and time in days on the x-axis. Now, to find the half-life of the graph, you basically want to look at what the activity was to begin with. So here, 80 counts per minute. Then find half of it. So 40 counts per minute is half of 80. And find out from the graph how long it takes to do that. That is 2 days. So the half-life, the time it takes for that activity to half, is 2 days. So, half-life equals 2 days. Be careful with your units. You need to make sure that you're, so I've used days here because the x-axis is in days, but you might have seconds, years, weeks, months, etc. So just be careful with your units. Right, half-life questions. So let's copy and paste this. And let's get rid of. Okay, so the way I made my year 10s lay these out is, so I'm just changing this. Okay, start, end, time, half-life. Now by that I mean, if you are given an activity or a count rate, what does it start at? What does it end at? You might be given both of those in a question. What is the time that has passed between that for the count rate to decrease, and what is a half-life? Now in a question you will be given 3 of those 4 pieces of information, and it's your job obviously to find the 4th. So let's read this question together. A radioactive material has a count rate of 1,600 counts per minute. So it starts off at 1,600. It has a half-life of 20 minutes. How long will it take to decay to a rate of 100 counts per minute? So you can see here, obviously I've got start, end, half-life, but I don't have the time. Now, in order to find the time, I need to work out how many half-lives there have been between the start and the end. And I do that by literally halving the start until I half and half and half and I get down to the end. So every time I half it, I draw a little arrow like this. So half it once, 800, then 400, then 200, and I'm just going to draw my arrows. The arrows are fairly important here. I know it seems a bit silly. Okay. So, there you go, 1,600, halves to 800, halves to 400, halves to 200, halves to 100. In order to work out how many half-lives there have been, you want to count the arrows. So here I've got 4 arrows, so there have been 4 half-lives. Then each half-life is 20 minutes, so the time, 4 half-lives, each one 20 minutes, is going to be 80 minutes. So you just do 4 times 80 there. Right, let's do another one and lay it out in the same way. Oh no, these are all very similar. Hang on. Apologies, I'm going to go find another. Can you find another half-life question? You can see all my folders here. Radioactivity. Half-life, go here. Oh, a little funny background. How bizarre. No, it's all the same. Come on. Come on. No, it's all the same. What is wrong with me? I thought I had others. Oh, do you know what? I'll just do it on notes. So be it. Okay, so. Let's type quicker. Plutonium has a half-life of 20 years. It doesn't, I've just made that up. If it starts with an activity of 2,500 becquerel, what will the activity be after 100 years? Okay, there's our question. So, again, we're going to lay it out the same way. Start, end, time, half-life. And do you know what? You could even put number of half-lives, because we used that in the other question, didn't we? Number of half-lives. But this is one you'll always have to work out, number of half-lives. So, activity of a half-life of 20 years, so 20 years. Starts with an activity of 2,500 becquerel. What will the activity be after 100 years? So time is 100 years. And we're obviously working out the end. So first thing is work out your number of half-lives. You've got 5 half-lives. That means I need to half 2,500 5 times. So 1,250. Next one, 625. Next one. Why did I pick such weird numbers? I know it's not exactly half, but I'm just going to roll with it to make life easier. There, 156, and then one more. What's that? 75, 78. Okay, I've halved it 5 times. I know that because I've done 5 arrows. The end is 78 becquerel. And that's it. So do you see, I lay it out. To get from start to end, you have to half it. The number of times you half it should be the same as the number of half-lives. Right, go away, have a go at some questions. I'll see you on Zoom later. Thanks, everyone.